Hello, my name is Jacob Can. I'm a senior at Virginia Commonwealth University, and I will be exploring duality, incidence, and projective geometry in this presentation. So we're going to start with a little bit of definitions and our background. We'll go to what it means for a theorem or a geometry to be self-dual. We'll look at projective geometries, Pascal's theorem, projective duals, Bryan-Kahn's theorem as an example of a projective dual of Pascal's theorem, and then Desargues' theorem on and how that's self-dual, significance of what we talk about, and then references. So duality is the principle whereby one true statement can be obtained from another by merely interchanging two words. And we see this in projective geometry, which we'll get to. Set theory, which is like set notation that we look at, like sets and what's in a set and combinatorics and permutations, symbolic logic, if and then statements in coding, but mostly we're going to be looking at projective geometries today. An incidence is a symmetric and reflexive relationship between two words. And this is important because it gets at the heart of how we define projective geometry. So say we have statement A. The point lies on the line. Point P lies on, that's the incidence part, the line L. And then statement B, the line contains the point. And we can sort of see that point and line are swapped, and then the two incidences are kind of opposite to each other, but they coincide with the relationship that is symmetric and reflexive. In this case, we say incidence I represents the meaning behind lies on, and I star represents the meaning behind contains. Taking the converse of I, which is I star, is the equivalent to finding the opposite statement, which represents the relationship when the words points and lines are swapped. More broadly, a converse overall of a statement is when the hypothesis and conclusion are swapped. So if Q then P becomes if P then Q. A geometry is a set of objects and a relationship on those elements. Euclidean geometry is what we're used to. Say you were told to draw a circle on a piece of paper in fourth grade. You were working probably in Euclidean geometry. A geometry can be considered as the geometry equals omega comma incidence, where omega is the set and I a relation which is both symmetrical and reflexive. In Euclidean geometry, omega of rank 2, like the second dimension, has the set of points P and lines L. A point in this geometry is incident to a line if it lies on the line, and two lines are incident if they have all points in common. So not all relationships between points and lines are incident, because not all relations are both symmetric and reflexive. But we can define geometry as the way that points and lines interact with each other in terms of their incidence relations. Suppose C represents a geometry, any type of geometry, where C equals points, lines, and the incidence between them. The converse statement, C star, the converse geometry, C star, is where we swap lines and points in the statement and use the inverse incidence accordingly. A self-dual geometry occurs when the converse of a valid incidence relation between points and lines are always true within the geometry. If that's the case, then the geometry is self-dual and C equals C star. It's the converse geometry is itself, and it is isomorphic if that's the case. This can also apply to statements, though, too. So a self-dual statement occurs if the converse of a valid statement regarding its incidence relation between points and lines is equivalent to the original statement. That means that the statement is self-dual. We don't need to do too much to show why the Euclidean geometry cannot be self-dual. And here's why. So in one situation, we see the line contains the point. In this case 1, the line A or whatever has this point in it. And that we call that relation line is incident to the point. And its converse is that the point lies on the line. And that works. Like we see that it's the same thing. It works out. But if we try to say 2 points determine a line, that might be case because A, B, you can always pass a line through that in Euclidean geometry. But if 2 lines intersect at a point always, that's just not the case, because you could have 2 parallel lines. They, in Euclidean geometry, would not meet at a single point. So all we have to do is show that there is a case 2, where taking the converse does not give a valid statement within that geometry. So we see that Euclidean geometry cannot be self-dual because within it, parallel lines never meet. We can, however, utilize a geometry that by definition accounts for this. Listed below are the axioms of projective geometry. And before I talk about them, it's important that we use axioms and not just kind of like a broad definition, because as like the different ranks of the geometries come into play, these axioms become more important for making sure that theorems hold and still work. So the axioms are very useful for that. Axiom 1 says that for every 2 distinct points, there's 1 distinct line incident to them. Axiom 2 states that if there are points A, B, C, D, such that AB intersects CD, then AC intersects BD. And all that's to say that any 2 lines of a plane meet. Axiom 3 is that any line is incident with at least 3 points. And that's kind of like the whole like 3 points are collinear. So you can't have a line basically that doesn't have 3 points. And axiom 4 is that there are at least 2 lines. We can also sort of define projective geometry as the study of the properties and invariance of geometric figures under projection. So this process of projection is where you have an image on the Euclidean plane, a light source at infinity that gives off parallel lines, and then as the light source passes through, say, like a semi-opaque picture of the image on that Euclidean plane, it projects a secondary image on the projective plane. And these follow different rules, this image on the projective plane, than it did on the Euclidean plane. You can also sort of view projective geometry and the projective plane as a sort of perspective drawing. So oftentimes infinity is represented by a horizon line, and you can see how these 2 railroad tracks are parallel, but they do meet, or so they appear to meet, at infinity, right, the little sunset. And so in projective geometry, 2 parallel lines intersect at a point at infinity. So we have theorems based on the world of projective space, and one such theorem is Pascal's theorem. And he came up with this when he was actually quite young. Given a hexagon inscribed in a conic section, the three pairs of the continuations of opposite sides meet on a straight line called the Pascal line. And so we can sort of see this line down here, that's Pascal's line. This is the conic, and a conic can be a circle, an ellipse, a hyperbola, or a parabola. It's sort of what happens when you take an ice cream cone and you take a sheet of paper and you slice it, and the image that you sliced it, if no matter how you could angle that piece of paper to slice it through, the edge of that circular conic section would come out to be as a circle, an ellipse, a hyperbola, or a parabola. So you can see that the hexagon is within the circle, that the points chosen on it, you continue them, and then you get your line. Normally this wouldn't work, right, in Euclidean geometry, because if you have a good old-fashioned parallel opposite sides hexagon, they're just gonna continue on forever. They're never gonna meet. You'd never get your Pascal line. So when we use this theorem in projective geometry, we're taking the horizon line as Pascal's line, and the points that they intersect are at infinity. And this is what ends up being the part that makes projective geometry so cool, is that suddenly you have these images that didn't work as soon as you put them in context with a perspective. A theorem including points and lines in two dimensions can be considered an incidence relationship between those points and lines. And so for any theorem in projective geometry, we get the principle that if you appropriately swap the terms for points and lines and adjust the wording to get the converse incidence, you get a second theorem, which is the first theorem's projective dual, and vice versa. The second theorem holds and is pretty much, you can just assume mostly that it's true within projective space, because it is self-dual. Pascal's theorem and Bryan-Kahn's theorem are one such example. If Pascal's theorem takes the form of line, points, and the incidence between them, then Bryan-Kahn's theorem takes the form of points, lines, and the converse incidence between them. So Bryan-Kahn's theorem is this: if you're given a hexagon circumscribed in a conic section, then the lines joining opposite polygon vertices meet in a single point. This is outside, this hexagon, unlike the other image, is outside the circle, but it doesn't make too big of a difference. I believe it has more to do with how they just defined it, the person themselves, in order to better arrive at a more cohesive image. Because if you took an hexagon on the inside, I'm sure you could pretty much get the same result. In this case, we are solving, however, for a single point. We're not creating Pascal's line. We're more concerned with a single point created from the lines of the hexagon itself and the points opposite to each other instead of the lines opposite to each other. We can see how they are similar with just looking at some images of them directly. Yep. And so here's Pascal's line, here's the point, here are the continuations of opposite line sides as lines versus continuations, the connection between opposite points. We also have Desargues's theorem as an example of self-duality. So we had projective space is a self-dual space, a self-dual geometry. Desargues's theorem gives us an example of a theorem that is also self-dual. So I'll get the image so it's a little bit clearer. We have let A, B, C, the triangle A, B, C, and A prime, B prime, C prime, this triangle, be two triangles in the projective plane. The lines A prime, this line, B prime, this dotted line, C prime, this dotted line, they all intersect at a single point. They are perspective to the point. If and only if the intersections of the corresponding sides, AB, this continuation line, BC, this continuation line, CA, this continuation line, they all go to the same line that the other triangle continuations also go to. They lie on this point, and this point of the line. They are perspective, both triangles are perspective to the line. This would be point P and line L. So in the prior slide, it wasn't totally clear how we're swapping the two different statements, the words in them, and we can see with a little bit of an altered definition how the theorem itself is self-dual. So for the first theorem, say if two triangles are perspective from a point, then they are perspective from a line. The converse is that if two triangles are perspective from a line, then they are perspective from a point. In this, we have the two triangles. They don't need to necessarily change because a triangle is self-dual with itself. We get the R perspective from a point and the R perspective from a line. We're really just taking the converse of the two statements. It's as if we're swapping the point, line, and that's it. That's all we really have to do because the incidence between them doesn't really change. We really just get an if and only if relationship. We don't get separate types of images and separate types of theorems like we saw how we're not determining something completely different with Pascal's line and Briancon's point. So why is it all important? What makes the projective plane so special? Under the right circumstances, the discovery of one theorem pretty much always implies the discovery of the second. And this is more or less just kind of like a neat trick. Some of the times it's sort of intuitive, but other times it's not, and so that can be kind of useful, and it gives a basis for more work to be done in the future. Duality applies to projective geometry, set theory, and symbolic logic. Coding is a really cool way to apply this, but that's not necessarily where it ends, and there might be more things that we just haven't found use for yet. And it's also cool because our human perspective is generally just how we see our world around us. And so to study projective geometry is to study Euclidean geometry, but in context of our physical surroundings and how we relate to it. It's kind of like when you hear people like, well, I'll never use this in the real world. Here it is, your projective plane, that's the real world. That's how we see things. It's just one step closer, and it used to be called projective geometry as higher geometry because it was thought to be the next step. And some of the more direct applications, you got to say a first-person shooter game, or that environment, that in-game world environment would do well to rely on the principles of projective geometry to create a greater sense of immersion. And like we saw with our perspective drawing, so too with a painting, a drawing, a piece of artwork. An artist would be informed by the relationships that come about from train tracks, from an object in that space, in context. So here's some references. Yep, and thanks for tuning in.